Hello everyone. I am Dr. Manisha Verma, teaching physics in Acharya Narendra Dev College, University of Delhi. Recently, I started a lecture series on thermal physics. In this series, I have already discussed what are heat engines, what are real gases, how are real gases different from ideal gases. After discussing the various experiments pertaining to real gases, I moved on to the kinetic theory of gases, wherein I derived the Maxwell's law of velocities. I discussed what is average velocity, what is RMS velocity, what is most probable velocity. After that, in my last lecture, I discussed what is the transport phenomena, what is its importance, and how does it give rise to various phenomena like viscosity, thermal conductivity, and diffusion. Today I will begin with a new topic, thermodynamic potentials 1. This is a very important topic in thermal physics, as you will see in a few moments. Now, what are thermodynamic potentials? First of all, that should be clear to us. What are thermodynamic potentials? What is the physical significance of thermodynamic potentials? How do we define the thermodynamic potentials? How do we apply the thermodynamic potentials? So basically, please understand one thing. When I am talking of thermodynamic potentials, I am missing out a word, thermodynamic potential energy. We don't call energy, but actually these are just energy. So what are thermodynamic potentials? These are the extensive state variables having dimensions of energy. What is their purpose? Their purpose is to allow for simple treatment of equilibrium for systems interacting with the environment. These functions are the energy functions formed by combining the basic thermodynamical variables. What does this mean? What are the basic thermodynamical variables? P, V, T, S. So all these potentials have these thermodynamical variables in various combinations, as you will appreciate in a few moments. So what are the thermodynamic potentials and how many thermodynamic potentials are there? So there are 4 fundamental thermodynamic potentials. 4. The first being internal energy. Internal energy is always represented by the symbol U. Second thermodynamic potential is the enthalpy or the total heat function. It is represented by the symbol H. The third thermodynamic potential is the Helmholtz function and it is represented by the symbol F. And the fourth and the last thermodynamic potential is the Gibbs function and it is represented by G. So these are the 4 thermodynamic potentials. Just as in mechanics, where potential energy is defined as the capacity to do work, similarly, different potentials have different meanings like the below. Internal energy is the capacity to do work plus the capacity to release heat. Now what is this? This is nothing but the first law of thermodynamics. Enthalpy is the capacity to do non-mechanical work plus the capacity to release heat. The Helmholtz energy is the capacity to do mechanical work plus non-mechanical work. Gibbs energy is the capacity to do non-mechanical work. Now let us discuss each thermodynamic potential in detail. So let me first take up internal energy. As mentioned just before, internal energy is represented by the symbol U. It is the energy possessed due to the kinetic energy and potential energy of the constituents of the system. This means that the internal energy of a system is the energy possessed due to the kinetic energy and potential energy of the constituents. The kinetic energy refers to the energy possessed by the molecules by the virtue of its motion, and the potential energy is due to the intermolecular forces of attraction. For an adiabatic process, dq is equal to 0. Now the first law says dq is equal to du plus dw. Actually, we should be saying delta q is equal to du plus delta w. Now, what is delta w? Delta w is pdv. So, we have delta q is equal to du plus pdv. For an adiabatic process, delta q is equal to 0. So, what do we get? We get du is equal to minus pdv. Now, let us consider an isochoric process. What is an isochoric process? Isochoric process is a process in which the volume doesn't change. This means that du is equal to 0. Thus, we have that the internal energy of a system is constant in an isochoric adiabatic process. So, if we have a process that is both adiabatic and isochoric, the internal energy of the system is going to remain a constant. If we combine the first and second law of thermodynamics, we have, instead of dq, we can write TdS, that is TdS is equal to du plus pdv. So, transposing du to the left hand side, we get du is equal to TdS minus pdv. Call this equation 1. This potential is also called isochoric isentropic potential, where thermodynamic potential is the internal energy U and the independent variables are entropy S and volume V. Now, why am I saying that the independent variables are entropy S and volume V? Because if I refer to the previous slide, you can see that du is equal to TdS minus pdv. So, we have ds and dv. It means we can say that u is a function of independent variables entropy S and volume V. This point is very important and is used while we derive the Maxwell's relations from the thermodynamic potentials. Now, let us concentrate and discuss on the second thermodynamic potential, which is the enthalpy. As mentioned before, enthalpy is represented by the symbol H. Let us consider a system and let us consider two states of the system, 1 and 2. Both these states are going to have different internal energies. So, let U1 be the internal energy of the state 1 and U2 be the internal energy of the state 2. In going from state 1 to state 2, if dq is the heat absorbed, then from the first law we have dq is equal to u2 minus u1 plus dw. If work is done at a constant pressure due to change in volume, then we can write dw as PdV or PV2 minus V1. Using this relation, in the previous relation, we have U2 minus U1 is equal to dQ minus P V2 minus V1. So, transposing various parameters, we get U2 plus PV2 minus U1 plus PV1 is equal to dQ. Now, by definition, U plus PV is defined as enthalpy. So, instead of U2 plus PV2, I can write H2, and instead of U1 plus PV1, I can write H1. So, what do we get? We get H2 minus H1 is equal to dQ. Now, when a system undergoes an infinitesimal process from an initial equilibrium state to a final equilibrium state, we have, since H is equal to U plus PV, we get dH is equal to du plus PdV plus VdP. Here we have applied the product rule on PV. Now, what does the first law say? The first law says that dQ is equal to du plus PdV. Using equation 3 in equation 2, we get dH is equal to dQ plus VdP. Let us divide both the sides of the above equation by dt. We then get dH by dt is equal to dQ by dt plus V dP by dt. At constant pressure, dP is equal to 0. So, what do we get? Delta H by delta T at constant P is equal to delta Q by delta T at constant P, which is Cp. What is Cp? Cp is the specific heat at constant pressure. This is an extremely important relation because, just let me reiterate, delta Q by delta T at constant V is Cv, and Cv is also delta U by delta T at constant V, whereas Cp is delta H by delta T at constant P. Now, just in the previous slide, we have seen that dH is equal to dQ plus VdP. What does the second law say? What is dQ? dQ is TdS. So, we get dH is equal to TdS plus VdP. During isobaric process, dP is equal to 0. So, we get dH is equal to dQ. During phase transitions, for example, melting, boiling, sublimation, the change in enthalpy will be equal to HF minus HI is equal to Q, or HF minus HI is equal to Cp dt. For an adiabatic process, dQ is equal to 0. Thus, what do we see? We see that for adiabatic and isobaric process, dH is equal to 0. Because what is happening in an adiabatic process? In an adiabatic process, S is a constant, so ds is 0. And what is happening in an isobaric process? P is constant, so dP is equal to 0. So, what do we get? TdS is equal to 0 and V dP is equal to 0. This means dH is equal to 0. So, what can we infer from this information? We can say that H is a constant when the process is both adiabatic and isobaric. Now this is very important. The process has to be both adiabatic and isobaric. It cannot be that the process is only one of the two. The potential enthalpy is therefore also called isentropic isobaric potential, and the independent variables in this case are entropy and pressure. Why? Because dH was TdS plus VdP. If you remember, in one of my lectures I had discussed the Joule-Thomson experiment. It was done when I was discussing real gases. So just let me connect the concept of enthalpy to that lecture. In a throttling process, that is the Joule-Thomson's experiment, enthalpy remains a constant. A process in which a gas at high pressure passes through a porous material into a low pressure region is the throttling process. During this process, U plus PV remains a constant, that is, enthalpy remains a constant. Now let us discuss the third thermodynamic potential, which is the Helmholtz function. This function is represented by the symbol F. From the first and second law of thermodynamics, we have TdS is equal to du plus dw. If the heat is exchanged between the system and surroundings at a constant temperature, instead of TdS we can write d of Ts, because T is a constant, can be taken inside the differential sign. Thus, the combined form of first and second law of thermodynamics takes the form du is equal to dTs minus dw. Transposing dTs to the left hand side, we get d of u minus Ts is equal to minus dw. The quantity U minus Ts is called the Helmholtz free energy or the work function, and it is represented by the symbol F. Now this means that F is equal to U minus Ts. Thus, for an infinitesimal reversible process, if we take the differentiation of both the sides, we get dF is equal to du minus TdS minus SdT. From the first law and the second law, we have TdS is equal to du plus PdV. So let us substitute the value of TdS into the previous equation. We get dF is equal to du minus du plus PdV minus SdT. Both the du's get cancelled and we are left with dF is equal to minus PdV minus SdT. At this stage, you yourself can make out that F is a function of two independent variables V and T. Thus, for a reversible isothermal process, we have dF is equal to minus PdV, because for an isothermal process, dt is equal to 0. If we integrate both sides, we get F final minus F initial is equal to minus integral PdV. Hence, we can say that the change of Helmholtz function during a reversible isothermal process equals the work done on the system. Now let us consider a process which is both isothermal and isochoric. That is, T is constant and V is constant. So what do we get then? We get dF is equal to 0, or this means F is a constant. Now very important, because dF is equal to minus PdV minus SdT, we can find out the expression for pressure and entropy using this relation. We get, by simple mathematical consideration, delta F by delta V at constant T will be equal to minus P, and delta F by delta T at constant V will be equal to minus S. The potential is also called isothermal isochoric function, where independent variables are temperature T and volume V, as just discussed in the previous slide. Now let us discuss the fourth thermodynamic potential, which is the Gibbs function. The Gibbs function is represented by the symbol G. For enthalpy, we have H is equal to U plus PV. Also, we have seen that dH is equal to TdS plus VdP. For isothermal and isobaric conditions, dH is equal to d of Ts, or dH minus Ts is equal to 0. Since the differential of H minus Ts is equal to 0, this would imply that the quantity H minus Ts is a constant. Let us define this quantity as G. This means that H minus Ts is equal to G is the Gibbs free energy. So what do we see? The Gibbs free energy is defined as H minus Ts, but H is U plus PV, so G is equal to U plus PV minus Ts. For an infinitesimal reversible process, we have dG is equal to dH minus TdS minus SdT. Also, dH is equal to TdS plus VdP. So, we have seen the various properties of the other various thermodynamic potentials. Gibbs function I will discuss more in detail. What is the physical significance of Gibbs function, under what condition the Gibbs function is a constant, and what are the independent variables. I hope you have understood the basic meaning of the thermodynamic potentials and how they are related to energies. Thank you.